Hey y'all. So at LSU, I feel like a lot of people are confused about comparing acidity and basicity amongst compounds. I remember I was definitely confused when I learned it, but I've actually learned it now. And what I want to do is make a video that tries to explain how to compare acids and bases. And the reason why this is important, especially for this chapter, is because with nucleophilic carbonyl substitution, um, so you have the nucleophile attack, and then after it attacks, it forms this tetrahedral intermediate. Then at this point, the weaker base leaves. So finding the weakest base is important in this mechanism. So we need to figure out how we're going to find the weakest base. So you have these definitions of acids and bases, and we've heard these in general chemistry, and it is kind of a history about it, so we're going to go through and keep up the tradition of going through each and every little one. So it starts with Arrhenius acids and bases, and what that has to do with concentration. So an acid increases hydrogen concentration in water, while a base increases OH concentration in water. So if we look at this, if you look at something like HCl, we put it in water, it will completely dissolve and then form all of these hydrogen ions, which will increase the concentration of hydrogens. Same thing if we look at the base, then we have the OH concentration increase if we put in NaOH, and so that's going to be a base by the Arrhenius definition. With the Bronsted-Lowry, we have, you're going to be looking at protons. So what happens here is that not all molecules increase the hydrogen concentration or increase the OH concentration directly. So what if we put in something like ammonia? Ammonia doesn't have any OHs on it, yet it still is a basic compound. So the important thing with Bronsted-Lowry is that it either donates or accepts protons. So an acid will donate protons, creating a lone pair of electrons, while a base accepts protons using a lone pair of electrons. So if you look at right here, if we have HCl, the HCl is donating this proton to the water molecule, creating H3O plus and Cl minus. While if we look at the base definition, then we have the ammonia donating a hydrogen to the water, or no, the water donating a hydrogen to the ammonia, and the ammonia using its electrons to accept that hydrogen, and then creating ammonium and OH minus. So here we start seeing that in these definitions you have an acid and you have a base. So right here your acid is your Cl, your HCl, and your base is your OH. This one will, so the thing donating the proton is the acid and the thing accepting the proton is the base. Here your base is ammonia and your acid is water. So the water is donating a hydrogen to the base of ammonia. And that includes most of it, but what if something is not in water? So, and it still has acid-base chemistry. So if you have two molecules that aren't dissolved in water, one donates a proton on the other, we still have acid-base chemistry occurring. So what's happening there is what's called the Lewis definition, and that's you look at the electrons. So an acid will accept electrons while a base will donate electrons. So if we look at the mechanism for acid-base of this HCl reaction, then we have the Cl, the effective part of the HCl, accepting the electrons from this hydrogen chlorine bond. So it then donates the proton, as the Bronsted-Lowry definition states it does. It donates the proton, and then this thing will donate its electrons to accept that proton, and that's how we create our H3O plus and Cl minus ions. If you look at the base one, you have these electrons donating to this hydrogen proton, and then the oxygen is then accepting these electrons from the oxygen-hydrogen bond. The oxygen's accepting it, creating OH minus and NH plus. So it kind of builds on itself in that everything that's a Bronsted-Lowry acid is an Arrhenius acid, and everything that's a Lewis acid is a Bronsted-Lowry acid, but not all things that are Arrhenius acids are Lewis acids, and not all things that are Bronsted-Lowry acids are Lewis acids. So it kind of improves the definition each step down the line. So that's what an acid is, all right? And you hear that, and like that's all cool, but the next thing that professors always harp on is the trends of the acids and bases stuff. So they always say that basicity goes up and to the left, and acidity goes down and to the right. A way that you can remember this is beans, B-E-A-N. So you have basicity, electronegativity, acidity, and then nucleophilicity. A lot of people know what electronegativity is because they know that fluorine's the most electronegative atom, or they tend to know that electronegativity goes up and to the right. So you know where like the E is in bean, and so you just got to remember B-E-A-N, go counterclockwise around it. Make sure that electronegativity is to the right, and then you have your trends. But basicity goes up and to the left, and then acidity goes down to the right. So what always confuses people, though, is that when you have something like NH3 compared to OH minus, the NH3 is more to the left than the OH minus, but the OH minus is more basic than the NH3. So this confuses a lot of people, and it definitely confused me. So because what I find that some professors forget to tell them is that the charges are also very important. So here we have the charges of these four elements right here: carbon, nitrogen, oxygen, and fluorine. And if you strip everything off of carbon and just have it in its natural state, it's a C4 minus. Now that doesn't exist because that's way too strong of a base to not interact with like anything. So a lot of these molecules don't exist, but like if we were just break it down, you have C4 minus, and if we add one hydrogen, we have CH3 minus. If we add two hydrogens to this, then we have CH2 2 minus. If we add one more hydrogen, we have CH3 minus, and if we add one more, then we have methane, CH4. And methane is a neutral molecule. Nitrogen, same thing's occurring. We're adding hydrogens as we go down. The only thing here is that the neutral thing happens when we had 3, while in methane it happened when we do 4. And when we do this for oxygen and then fluorine, what you'll find is that you get one less hydrogen for the neutral compound as you go up, so or as you go more to the right. So this one has CH4, then NH3, then H2O, then HF. And these are like the neutral compounds, the one without the charges. The ones with the charges are just one less hydrogen, so that's these four right here. And then the ones with positive charge are right here. So I took the neutral ones and put them right here in this chart. The ones with the negative charges in this one, and the ones with positive charges in this one. So that's just like what these two graphs are. What's important to note here is that if you have a negatively charged species, it will always be more basic than any neutral compound. And then if you have a neutral compound, it will be more basic than a positively charged compound. And then, of course, your -1 is going to be more basic than your +1. Now, when comparing things that all have the same charge, so CH3 minus compared to CH2 minus, you use that trend that we talked about here, in that it's more up and to the left. But if you are comparing like CH3 minus to CH4, then CH3 minus wins because it has a negative charge. Now, one thing that's important to note is that there needs to be free electrons to be a base. So like something like CH4 is not going to have basic properties because it can't expand octet and it doesn't have any electrons to donate to correspond to our definition of base. You know, a base has to donate electrons, and if you don't have any electrons to donate, then you don't have basic characteristics. So now if we look at our NH3 compared to OH minus, then we see that the OH minus is more basic than the NH3 because it has that negative charge, right? And so it's about comparing, when you're comparing things that all have the same charge, it's up and to the left. But when you're comparing things with different charges, it's about which is more negative. Now technically, what you're supposed to be doing to compare these things is look at the pKa values, and the lower the pKa, the lower pKa will protonate the one that is higher pKa. So in these reactions, you'll look at something that has a pKa of 5 compared to something with a pKa of 7. You'll know that the one with the lower pKa, the pKa of 5, will then protonate the thing with higher pKa of 7. But in organic chemistry, we don't typically do stuff like that. That's more for general chemistry. Now, you could absolutely do that. But with regards to this class, it's we tend to look at these trends. So the next step that we look at is the conjugates. I'm just going to go over this briefly. A molecule has like a natural state. And if it loses a proton, then it becomes negatively charged. And if it gains a proton, it becomes positively charged. Now, if it loses a proton, it has a free electron pair now. And so you have less or no protons to then give away. And so this is called the conjugate base. And if it gains a proton, then it becomes positively charged. It has a proton that it can donate now, but it has less electrons or no electrons. And so this is what's called the conjugate acid. And I'm going to get a picture for y'all to explain it. So here, right here, we have HCl and H2O. So H2O is like the molecule in its natural state. Now when it gets protonated, the proton goes from the Cl to the OH. This is now has a positive charge and less electrons, so it is less basic and it's more acidic. It is the conjugate acid of H2O. This right here, the Cl minus, is the conjugate base of HCl. So this thing can now act like a base because it has a negative charge, and this thing will act like an acid because it has a positive charge, and now can donate these protons. Right here, we have water acting as, we can see, its conjugate base. So here, again, it's donating its proton to the nitrogen. The nitrogen's taking off the proton, and it's accepting the electrons. So now that it's accepting the electrons, it's got a negative charge, and so it can act as a base relative. And then this thing, now that it has more protons, can act as an acid. So to sum it up, you want to be looking at the stability of conjugates. So the more stable the conjugate base, the stronger the acid, and the more stable the conjugate acid, the stronger the base. So if you look at these things, you can compare the relativity of the using your trends and your knowledge of charges. Now you can compare the conjugate acids and conjugate bases, and so that's acid-base chemistry. The next video will show how you can use these things in reactions.